stream has started, but the broadcasting is not yet happening, so I'm gonna wait for that to start. Meanwhile, hello, friends. Welcome to not really live coding, I guess. We're not gonna be doing any coding today. We're gonna be reading a paper. And by reading a paper, I mean continuing to read a paper. All right, excellent. Everybody has begun streaming. Just gonna double check my audio because I had some problems a couple streams ago. That looks good. Welcome to part 2 of this paper reading group. Hey, Akshay, good to have you back. The paper is a primer in BERTology, what we know about how BERT works, by Anna, or maybe Anna, Rogers, Olga Kovaleva, and Anna, or maybe Anna Rumshiski. Again, my apologies if I ever mispronounce somebody's names. It is me. That's my fault. That's not on whoever's name it is. Hello, Gutham. Excuse me. Am I done? A little sip of coffee. That's cold. That is cold coffee. It was brewed hot though, so it doesn't taste bad. All right, so we started last week. Last Wednesday. We read through the introduction, which was a quick overview of the BERT architecture. We talked about the embeddings and what we know about BERT embeddings as opposed to other types of word embeddings. We talked about the syntactic and semantic knowledge that BERT has, which is kind of none, but if you squint right and do some transformations, you can extract some correlates of it from the BERT models. We talked about the world knowledge, which again, BERT does not have any. This is not a grounded model. And then we talked a little bit about starting to look at the attention and self-attention. So, some of the key findings from this section, a lot of the heads on any given sort of task or item actually seem to be turned off and show this vertical attention pattern, where the attention is on these SEP tokens, which are the tokens between, between sentences or between, turns of a dialogue, if that's how you're using it or however you're structuring it. And this pattern, this vertical attention pattern, seems to be off more or less, and over half of the heads are off at any given point. And also for heads that do seem to be attending to things like syntax and syntactic patterns, you can remove those and it doesn't matter. So I think the way that I would sum up what we've read so far is this is not human-like. The attention that BERT's attention weights are not similar to human attention. Or they're similar in some ways, but not in the important ways. She says, need video on research ideas with NLP and chatbot. Yeah, that's an interesting suggestion. It's always... Like I get actually kind of a lot of requests for ideas for research projects, and my suggestion is always the same. Keep reading research papers, related research papers, until you come up with a question, until you're like, oh, so they did this, but what would happen if we did that? Or, well, have they tried this yet? And if they haven't, what would happen if we tried that? And I know that, of course, the research institutions work very differently in different places, but at least in the United States, you can sort of pick your own research questions, and the more invested you are in finding the answer out, easier it's going to be to finish papers, which is sort of the point. So that's my general suggestion for coming up with research ideas. All right, and then we finished off with section 5.2, so let's jump back in. And that is, how long was that? That was a 5-minute intro, not too bad. Okay, BERT layers. The first layer of BERT receives as input representations that are a combination of token, segment, and positional embeddings. So token is, I actually did go back and skim the BERT papers just so I had a better understanding here. So token is a ID for the byte pair encoded word piece token, and if that means nothing to you, that's okay. Segment is whether it's in the first or the second sentence or turn, or whatever is separated by the separated SEP tokens. And then positional embeddings are these weird sinusoidal way of saying which word occurs at which position. I still am not entirely sure why that's better than an indexed-based embedding. But, yeah. If someone has suggestions for that, I'd be interested in hearing them. Oh, excuse me. I think I'm allergic to something that's blooming right now. All right. It stands to reason that the lower layers have the most linear word order information. Lin et al. Report a decrease in the knowledge of linear word order around layer 4 in BERT base. This is accompanied by increased knowledge of hierarchical sentence structure, as detected by the probing task of predicting the index of a token, the main auxiliary verb, and the sentence subject. So there's, I think someone did this for GPT-2. There's been some work on transformers that suggests with like multiple layered transformers, lower layers are more local, higher layers are more long range. And I think this is just, this might actually be the paper that I read that also looked at GPT-2. It's been a while. There's wide consensus among studies with different tasks, data sets, and methodologies that syntactic information is the most prominent in the middle BERT layers. Hewitt and Manning had the most success reconstructing syntactic tree depth from the middle BERT layers, 6 to 9 for BERT base BERT, 14 to 18 for BERT large. I believe there are 12 layers in base BERT and 24 in large. Pankaj says, I will at last complete the paper thanks to you. I have been procrastinating it from last week. Yeah, it's really easy to procrastinate reading papers, which is why I am doing this with you guys, because I can't procrastinate if I'm scheduled to do it at 9. Goldberg, 2019, I think that's Yoav, reported the best subject-verb agreement around layers 8 to 9, and the performance on syntactic probing tasks used by Jawahar et al. 2019 also seemed to peak around the middle of the model. The prominence of syntactic information in the middle BERT layers must be related to Liu et al.'s observation that the middle layers of transformers are overall the best performing and most transferable across tasks. Oh, interesting. So my understanding from the literature, and BERT is not my main research area. I don't really have a main research area right now, but I have been reading more about smaller models that are transformer based, like Convert, that we talked about in NLP for Developers a couple times ago. And that's interesting. I would have guessed that what would I have guessed the top layers were best at? I would have guessed that the top layers were best at next sentence prediction, because that's the longest range task that BERT is asked to do, and that the first layers would be better at the masked language modeling task. So I guess it makes sense that the middle layers are doing things between masked language modeling and next sentence prediction. But okay, but this also could just be a just so story that I'm telling myself and is not in fact the case. So that seems like a plausible hypothesis that I am not wedded to. All right, there is conflicting evidence about syntactic chunks. Tenney et al. 2019a conclude that the base syntactic information appears earlier in the network, while high-level semantic features appear at the higher layers, drawing parallels between this order and the order of components in a typical NLP pipeline, from part-of-speech tagging to dependency parsing to semantic role labeling. I think this is the paper I read. Jawahar et al. 2019, I don't think I've read that, also report that the lower layers were more useful for chunking, while middle layers were more useful for parsing. At the same time, the probing experiments by Liu et al. 2019a found the opposite. Both part-of-speech tagging and chunking were also performed best at the middle layers in both BERT base and BERT large. Oh, interesting. Okay, so I'm going to take the little theory I just talked about the order of layers and put it on a little peg that says maybe. Because it looks like there's not a lot of consensus here from the literature about where in the trained weights this information is the most important. All right. These BERT results are also compatible with findings by Vig and Belenkov, 2019, who report the highest attention to tokens in dependency relations in the middle layers of GPT-2. Okay, and I might have skimmed that. I don't know. At some point, you just have a hard time remembering what you've read, and I don't keep a good citation database anymore. Used to have a really good one for my graduate work. So maybe I should start doing that again. All right, so not entirely clear where in the model the greatest amount of syntactic information is. The final layers of BERT are the most task-specific. In pre-training, this means specificity to the masked language modeling task, which would explain why the middle layers are more transferable. In fine-tuning, it explains why the final layers change the most. At the same time, Howe et al. 2019 report that if the weights of lower layers of the fine-tuned BERT are restored to their original values, it does not dramatically hurt the model performance. Interesting. Okay, so I mentioned that the first layers might be more useful for the masked language modeling, and it looks like they are not, which I guess makes sense because that's actually a fairly long-range task. So I can update my beliefs there. Base joke. And this is sort of consistent with a lot of the work that I've come across, which is that BERT base and BERT large are bigger than you need them to be. You can remove a lot of the model and still have really good performance. So this does not, so basically this is just saying that you fine tune the model and then you go back to the lower layers and then just reset the weights so that they weren't tuned at all, and that does not change model performance much at all, which suggests that you shouldn't bother tuning them because that's compute down the drain. Well, I mean, compute for not a very useful purpose. Tenney et al. 2019a suggests that while most of the syntactic information can be localized in a few layers, semantics is spread across the entire model, which would explain why certain non-trivial examples get solved incorrectly at first, but correctly at higher layers. This is rather to be expected. And what they mean by that is for like the masked language modeling, if you get a prediction after like layers, let's say 1 through 4, you'll get one prediction that's incorrect. But if you go all the way to layer 12 for BERT base, you'll get a correct prediction. So it sort of like changes its mind as it percolates up through the model. This is rather to be expected. Semantics permeates all language, and linguists debate whether meaningless structures can exist at all. So there's a pretty core idea in generative syntax that syntax, like structure and meaning, are separable. But also there are people who would say that that is not true. So I would agree that there is a debate. Neversad said, morning, you said earlier on there were other algorithms easier to use instead of BERT. What are those? So if you're really set on, for conversational AI right now, I'd recommend Convert, which I did a YouTube video about on the Rasa channel. In general, I would recommend smaller versions of the model. So Albert, which I think is by the same authors, actually is smaller. Distilbert is smaller. There's just lots of sparse transformer-based models are smaller. They're just, cheaper to store, cheaper to run, cheaper to train. So that's my general suggestion. Black White Life says, why do you read papers? Isn't it boring? No. I read papers so that I don't have to reinvent the field of NLP from scratch myself, because that's not a good use of my time on this planet. All right. This raises the question of what stacking more transformer layers actually achieves in BERTs in terms of the spread of semantic knowledge, and whether that is beneficial. The author's comparison between base and large BERT shows that the overall pattern of cumulative score gains is the same, only more spread out in the large BERT. Overall pattern of cumulative score gains. So the improvement... Okay, so I'm guessing that this is where in the model does the improvement happen, and the pattern of improvement is the same, except it is more spread out in BERT because it's larger. Black White Life says, what are your goals and ambitions while on this planet? I've actually been thinking about that a lot this year, and my mission statement right now is to help people build language technology that radically improves people's lives and increases equity and justice. So that's my personal mission statement right now. The above view is disputed by Jawahar et al. 2019, who places surface features in lower levels, syntactic features, something is ringing, who places surface features at lower levels, syntactic features in middle levels, and semantic features in higher layers. Maybe I did read this. However, the conclusion with regards to the semantic features seems surprising, given that only one cent-eval semantic task in the study actually topped at the last layer. The other three peaked around the middle and then considerably degraded in the final layers. Interesting. Akshay says, should we try to implement the newer models from scratch to get a better understanding of it working, or should I just use it without caring what goes inside? In general, I don't recommend re-implementing very large models from scratch because it is extremely expensive, like many, many thousands of dollars worth of compute expensive. And also, like if you are doing it for your learning, that's not necessarily a great use of resources in general. Maybe like a small model if you find that helpful. I think my preferred method of choosing which model to use is to read about and to learn about the benefits and drawbacks of the different models and then pick the one that's best for me. But as a sort of a corollary, I think in the last 10 years, people have stopped pretty much training their own word embeddings from scratch because the gains from pre-trained word embeddings are pretty good, and again, it saves you time and money. And I think the language modeling shift is also sort of taking that, instead of using just pre-trained word embeddings, you're using pre-trained contextual word embeddings that includes the language modeling, which is sort of the big deal with Bert. Not that Bert is the first system to do that. So I think you should care about what goes inside. I think there are better ways to learn that than training it from scratch, if that's a good answer. All right. Interesting. So my sort of idea that I had that like the structure goes up as you go up the transformer layers also seems to not necessarily always be the case. There's some evidence that sometimes it is, and then a lot of the time it isn't, is what I'm getting from these paragraphs here. Training Bert. This section reviews the proposals to optimize the training and architecture of the original Bert. Pre-training Bert. The original Bert is a bidirectional transformer pre-trained on two tasks: next sentence prediction, NSP, and masked language modeling. What makes it bidirectional? So transformers do not care about order like an RNN does. A model like Elmo trains two RNNs, one going forward and one going backwards. Bert is bidirectional because it looks at all of the words in the context, basically. Akshay says, thank you. I've been debating myself over this for the past 2 weeks. Yeah, that's fine. Hi. Is it Anna or Anna? I don't actually know how to say it. I'm sorry. And thank you for joining. So the first author of the paper has popped in. So thank you. All right. Multiple studies have come up with alternative training objectives to improve on Bert. Removing next sentence prediction does not hurt or slightly improve task performance. Does not hurt or slightly improves task performance. So it looks like the next sentence prediction is not actually that important, and then there's multiple studies looking at that, especially in cross-lingual setting. Wang et al. Replaced next sentence position with the task of predicting both the next and the previous sentence. Lan et al. 2020 replaced the negative NSP examples by the swapped sentences from the positive examples rather than sentences from different documents. Okay, so they're saying that instead of taking a sentence from a different document and saying, it does this come next, they take a previous sentence from the same document and said, does that come next? Okay. Dynamic masking, Liu et al., improves on Bert's masked language modeling by using diverse masks for training examples within an epoch or epoch. Diverse masks. So that could be the way that Bert is done, there's one token mask that's used to replace the word, and I don't know if this is using different tokens there, or if they're on each pass changing which words are masked. Probably the second one. That sounds like what that's saying to me. Beyond sentence masked language modeling, Lampel and Kano replace sentence pairs with arbitrary text streams and subsample frequent outputs, similar to Mikolov et al. Replace sentence pairs with arbitrary text streams. Okay, I'm guessing that's like text that's in the same order as the original text, but they're not chunking it based on sentences. They're just taking a selection of text, I guess, is what that says to me. Permutation language modeling. Yang et al. 2019, Yang et al. Replaced masked language modeling with training on different permutations of word order in the input sequence, maximizing the probability of the original word order. See also the n-gram word order reconstruction task, Wang et al. 2019a. I'm pretty sure I have read this. Nope, definitely have not. Oh, XLNet I have. But I have definitely not read this one about training Bert in 76 minutes. So, might be a useful paper. Scroll. I went too far. Continual learning is sequential pre-training on a large number of tasks, each with their own loss, which are then combined to continually update the model. New token level tasks in Ernie, also a Sesame Street character, include prediction whether a token is capitalized and whether it occurs in other segments of the same document. Segment level tasks include sentence reordering, sentence distance prediction, and supervised discourse relation classification. Sentence distance prediction. Oh, that must be how far apart it is in the text. So like, that word and that word are farther apart than this word and this word, I'm guessing. Okay. And that sounds sort of like multitask learning. Actually, it sounds a little bit similar to the diet architecture that we have developed here at Rasa. Conditional masked language modeling by Wu et al. Replaces the segmentation embeddings with label embeddings, which also include the label for any given sentence from an annotated task dataset, e.g. sentiment analysis. So the embeddings are the token embedding, the positional embedding, and then the segment embedding, which is just like first input, second input. And instead, they're replacing those segment embeddings with things like sentiment score. Gutham says, I think you missed a few paragraphs. I absolutely did. Thank you. Hi, Ravi. Okay, yeah, I don't think I've read this one. Span boundary objective aims to predict a masked span rather than single words using only the representations of the tokens at the span's boundary. I wonder how well that works. Interesting. Phrase masking and named entity masking aim to improve representations of structured knowledge by masking entities rather than individual words. And then this one, Clinchant et al. Proposed replacing the mask token with UNC token, so UNK means unknown or out of vocabulary, as this could help the model to learn certain representation for unknowns that could be exploited by a neural machine translation model. Interesting. Okay, so I personally would probably say that the main contribution of the Bert paper was the masked language modeling training paradigm. And there have been a lot of variations on that. Another obvious source of improvement is pre-training data. Liu et al. 2019C explores the benefits of increasing the corpus volume and longer training. The data also does not have to be unstructured text. Although BERT is actively used as a source of world knowledge, there are ongoing efforts to incorporate structured knowledge resources. So this would be like WordNet, or I mentioned last time that you can like hand build databases about the structure of words and how they relate to each other in the world. Robbie says, we're students, you can debate with her. Y'all can debate with you. Me, you're not my students. I'm not grading nobody. Another way to integrate external knowledge is to use entity embeddings as input, as in eBERT and Ernie. Entity embeddings. What's an entity embedding? I'm not familiar with that. Do a little quick Google. See if I can find out. Entity embedding. I found a Git repo for doing entity embedding, so let's take a look. This is the code used in the paper Entity Embeddings of Categorical Variables. If you want to get the original version of the code used for the Kaggle competition, please the Kaggle branch. Oh, Kaggle. I used to work for Kaggle, for those of you who don't know. Affinity propagation says embeddings to categorical embeddings as far as I know. Hello, by the way. Hi. Interesting. Okay. You could blah, 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 blah. The following the learned embeddings of German states printed in a 2D map and a map of Germany side by side. Considering the algorithm knows nothing about German geography, the remarkable resemblance between the two demonstrates the power of the algorithm for abductive reasoning. Oh, that sounds a little bit like a Just So story. Just So stories are basically a post hoc analysis that like sounds good given the information that you've given, but that you didn't have a strong reason to believe would be the case beforehand. And it comes from Rudyard Kipling's stories of like fables that he made up. Maybe I should stop saying that. He was not the best person. Okay, so map of Germany, visualization of embeddings. Not super helpful. Anna says, entity embeddings are just separately learned embeddings that represent entity knowledge, usually from Strum's structured resource. Oh, I see. So instead of being trained from unstructured text, it would be from, like, WordNet or something. Okay, that makes sense. All right, pre-trained weights help Bert find wider optima in fine-tuning MRPC right than training from scratch. I'm assuming we haven't gotten to that bit yet. Was there a reference to figure 6? Oh, hasn't yet. Pre-training is the most expensive part of training Bert, understatement, and it would be informative to know how much benefit it provides. How et al. 2019 conclude that pre-trained weights help the fine-tuned Bert find wider and flatter areas with smaller generalization error, which make the model more robust to overfitting. However, on some tasks, a randomly initialized and fine-tuned Bert obtains competitive or higher results than the pre-trained Bert with a task classifier and frozen weights. Interesting. Interesting. Okay, so one of the things that I mentioned last week that I've just been thinking a lot about is this distinction between the architecture and the model. And usually when people say BERT, they mean BERT base or BERT large, the like trained model. And this suggests, and just a quick recap if you're haven't used BERT a whole lot, the way it works is that there's this it's like a sequence-to-sequence encoder-decoder structure, except there's no decoder. So you just get the output of the encoder, and then you use that as embeddings to pass into your final classifier, and then you do fine-tuning based on the classifier. Fine-tuning, sorry, based on the classifier. And the pre-training Oh, I used to know off the top of my head. I want to say it took something like an estimated $16,000 worth of compute to pre-train Bert base. And there's a lot of discussion about this on Twitter, and I don't think Google's released the numbers. I think it's just like people with back-of-the-envelope math based on how much compute time they used and what cores. And this suggests that what you're getting, so the How Adult paper suggests that what you're getting for pre-training is a more a better large sort of approximation of the decision region, that you're less likely to get into sort of get stuck, as it were. And this paper suggests that the pre-training is not actually that important, and a randomly initialized model, which I would say is the closest you can get to being like, here's what just the architecture is, and the effect of just the architecture, as opposed to here's what the pre-trained model does about as well. So that suggests that it is, in fact, the specific architecture that's giving you the benefit, not necessarily or not just the spending a lot of time in compute extracting these correlates from unstructured text. That's really interesting. All right, model architecture choices. To date, the most systematic study of BERT architecture was performed by Wang et al. 2019. They experimented with the number of layers, heads, and model parameters, varying one option and freezing the others. They concluded that the number of heads was not as significant as the number of layers, which is consistent with the findings of Voida et al., Michel et al., discussed in section 7, and also the observation by Liu et al. That middle layers were the most transferable. Okay, so I believe that the number of heads in BERT base is 7? And it looks like you can reduce that quite a bit and still get good results, but you do need more layers, and more layers benefits is what I'm getting from this. Larger hidden representation size was consistently better, but the gains varied by setting. Interesting. Okay, so the bigger your hidden layers and the more weights you learn, well, or the more weights you initialize, I guess, maybe not necessarily learning. And it says 12 heads, 12 layers. Okay, so it was not 7. I definitely made that up off the top of my head. Oh, or maybe it was 7 in the Vaswani paper. Thank you. It's really helpful having you in the chat. All right. So bigger models better, but you don't get the same gains from increasing size everywhere. So deeper is better than more heads. Liu et al. 2019 C, excuse me. Well, I guess the BERT paper was released by press release as opposed to peer review in 2018. So I guess you could get a 2018 paper if it was a late one. Liu et al. Show that large batch training, 8K examples, improves both the language model perplexity and downstream task performance. Perplexity is a way of measuring language models from information theory that looks at the amount of entropy in the model, and I always get it backwards, so I'm not going to say what it is in terms of words. I always get perplexity and information and entropy backwards. They also published their recommendations for other model parameters. Yu et al. 2019 report that with a batch size of 32K, BERT's training time can be significantly reduced with no degradation in performance. Zhao et al. Observes that the embedding values of the trained CLS, that's the classification, token, are not centered around 0. Their normalization stabilizes the training, leading to a slight performance gain on the text classification tests. Interesting. Okay, so this is saying that the classification tokens are sort of like somewhere in the decision space where 0 is not the center of the cloud, and moving them so that 0 is the center of the cloud gets you slightly better performance on text classification texts, is I think what they mean by normalization there, and not taking those and transforming them into a normal distribution or a Gaussian around 0. Because that second thing is what I would think if a stats person said that, but because this is an ML paper, I think it's probably the first thing and they're just moving them in space. Could be wrong about that. Would have to read the paper. Gong et al. Note that since self-attention patterns have in higher layers resemble the ones in lower layers, the model training can be done in a recursive manner, where the shallower version is trained first, and then the trained parameters are copied to deeper layers. Such warm start can lead to 25% faster training speed, while reaching similar accuracy to the original BERT on glue tasks. Interesting. So I think the main thing that I would say from this entire section is that the original architecture has a lot of redundancy in it, and the redundancy that's, well, not redundancy, and the size increase that's important is the number of layers. Hello, John. Fine-tuning BERT. Pre-training and fine-tuning workflow is a crucial part of BERT. The former is supposed to provide task-independent linguistic knowledge, and the fine-tuning process would presumably teach the model to rely on the representations that are more useful for the task at hand. Kovaleva et al. Did not find that to be the case for BERT fine-tune on glue tasks. During fine-tuning, the most changes for 3 epochs or epochs occurred in the last 2 layers of the model, but those changes caused self-attention to focus on SEP rather than on linguistically interpretable patterns. Interesting. Akshay said underfitting. So if you do need, so just to clarify what I think you mean here, so I mentioned there's a lot of redundancy in the model, and I think what you're implying is that the redundancy is, it seems redundant because we're not spending enough time, or we don't have enough data, or we're not training the model sufficiently to correctly use all those parameters, which could be the case. I would say that BERT already uses, honestly, more data and compute that I'm entirely comfortable with. I don't know, I've been thinking a lot about the sort of climate impacts of training really, really large language models, especially multiple teams training competing language models that are, you know, kind of different architecturally, but also kind of the same. I'm all about small models. That's the whole thing. And even if it is underfitting, I want a model that fits quickly and isn't big and expensive. You know, I like small things. I want a little mini model that just like works real well. That's what I want. Yeah. Anyway. Okay, so what this is saying is, so the whole idea of BERT is that you have these pre-trained weights and that they sort of like approximate knowledge of the language and having read a lot of text, and you can use those and fine-tune them for specific tasks. This work suggests that what fine-tuning is doing is it's actually sort of turning off some of the layers in the last, so it's turning off a lot of the weights in the last layer of the model, or the attention head specifically, because that's the pattern, like the vertical attention pattern seems to be just like, oh, I'm not important here, I'm just gonna whatever. And that's not, you know, it's not doing things in a languagey type way or the way that a human would do things with a language. It is understandable why fine-tuning would increase the attention to the segment that we use for classification. That makes sense. Not the segment between sentences or inputs. If Clark et al. Are correct that SEP serves as a no-op indicator, fine-tuning basically tells BERT what to ignore. That's a better way of saying it than I just said it. Several studies explore the possibilities of improving the fine-tuning of BERT. Where is this from? Oh, on the glue tasks. See also experiments with multilingual BERT by Singh et al. 2019, where fine-tuning detected the top and middle layers of the model. Interesting. So one thing that you could do is take more layers into account. Yang and Zhao learned a complementary representation of the information in the deeper layers that is combined with the output layer. Su and Cheng propose using a weighted representation of all layers instead of the final output layer. So the way that usually you would use BERT is you would take your input, run it through the model, take the output layer, and they're saying instead of doing that, just taking the last layer, taking sort of like an average across all layers so that you get more use of the lower layers. Two-stage fine-tuning introduces an intermediate supervised training step between pre-training and fine-tuning. So there's like a second stage of fine-tuning, and then adversarial token perturbations improve robustness of the model. So like every so often you just lie a little bit. Zhu et al. With larger and larger models, even fine-tuning becomes expensive, but Holsby et al. 2019 show that it can be successfully approximated by inserting adapter modules. That sounds like a video game thing. They adapt BERT to 26 classification tasks, achieving competitive performance at a fraction of the computational cost. I don't know what an adapter module is, but it sounds like it makes things cheaper, so I am absolutely on board for that. ArtXC, I could not even tell you what language that is from. Maybe it's Mesoamerican. Could be Basque. Also find adapters helpful in reusing monolingual BERT weights for cross-lingual transfer. An alternative to fine-tuning is extracting features from frozen representations, but fine-tuning works better for BERT. Okay, so instead of using just like the pre-trained weights and then using them like word embeddings, using a little bit of fine-tuning so that you generate new weights seems to be a little bit better. Initialization can have a dramatic effect on the training process, Petrov 2010. However, variation across initializations is not often reported, although the performance improvements claimed in many NLP modeling papers may be within that range of variation. Dodge et al. 2020 reports significant variation in BERT fine-tuned on glue tasks, where both the weight initialization and training data order contribute to the variation. They also propose an early stopping technique to avoid full fine-tuning for the less promising seeds. And this paper is on my to-read list as of yesterday. Nami says, I like the crawfish video game, Crawfist. And Anna says about adapters. Adapters are small layers you insert between the layers of a larger model. You then freeze the larger model and train only the adapters. Okay, so it sounds a little bit like gating almost. Some similarities. Okay, interesting. Cool. Learned something new today. So about this, there's a part in the BERT, like the original BERT paper, where Devlin and co-authors, I don't know who wrote what part of the paper, talk about some proportion of their fine-tuning runs were just degenerate, never converged. And it just seemed to depend on what random seed they used. And I don't think they report what proportion had that problem, but it does seem to, having talked with other like practitioners and people who are trying to fine-tune BERT for various tasks, it does seem to be a pretty common problem with this sort of transformer-based model that you do fine-tuning on. And that's, don't like that. Don't like unexplained instability. Yeah, not a huge fan of that, the fact that that exists or that there's so little work on it. So this Dodge paper is absolutely on my to-do list. How big should BERT be? Smaller than it is, probably, is my one-word answer to that. That's not a word. Overparameterization. Transformer-based models keep increasing in size, e.g. T5, Wu et al. 2016a, is over 30 times larger than base BERT. Is the date right on that? I think that should be 2019. I think the date's wrong on that. Yeah, okay. I'm pretty sure that's supposed to be 2019 and not 2016. Because I vaguely remember reading about T5, and I think it was more recent than that. 2016, I would have still been in my PhD program. Also, this is why I don't like citation styles that do not include the date next to when the date next to the paper, because then I can place things in a chronological order, and that's important for scholarship. It says, yes, wrong date, sorry. Okay, good. I had a moment where I was like, wait, it could have been 2016. I don't mean to harp on typos. I don't think I've ever published a single paper or poster without at least one typo in it because I'm dyslexic. I was just confused. Blah, blah, blah. This raises concerns about the computational complexity of self-attention, environmental issues, as well as reproducibility and access to research resources in academia versus industry. All things that I think about. And also, I mean, even, looking across industry and across academia, not everyone has access to the same resources and can just, spin up, 100 TPUs to run overnight. So, human language is incredibly complex and would probably take many more parameters to describe fully, but the current models do not make good use of the parameters they already have. Voida et al. 2019 showed that all but a few transformer heads could be pruned without significant losses in performance. For Bert, Clerk et al. 2019 observed that most heads in the same layer show similar self-attention patterns, perhaps related to the fact that the output of all self-attention heads in the layer is passed through the same MLP, which explains why Michael et al. Were able to reduce most layers to a single head. MLP, multi-layered perceptron, probably like a feed-forward network. Depending on the task, some Bert heads layers are not only useless, but also harmful to the downstream task performance. Positive effects from disabling heads was reported for machine translation and for glue tasks, both heads and layers could be disabled. Additionally, Tani et al. 2019 examined the cumulative gains of their structural probing classifier, observing that in 5 out of 8 probing tasks, some layers can cause a drop in scores, typically in the final layers. Yeah. So maybe it's not necessarily that Bert is too big and that it could be as big as it is, but it should be doing better for as big as it is. Many experiments comparing Bert base and Bert large saw the larger model perform better, but that is not always the case. In particular, the opposite was observed for subject-verb agreement, Goldberg, and sentence subject detection, Len et al. 2019. Yeah. So this is sort of an interesting departure from a lot of the... So since people started using deep learning models for NLP, there's been sort of this consistent trend where bigger models are better, and more parameters equals better performance. Certainly for RNNs, that seems to be the case. But a lot of the sort of work after Bert came out and on transformer architectures in general suggests that that's not necessarily the case. Gutham says, can you translate with Bert since it doesn't have a decoder part? I think you'd need to add a decoder. But I mean, it's like half of a basic sequence to sequence model. So you could use it as an input to a decoder. And people have definitely used it for machine translation, so if you're interested, I would search for code samples and work off of those. That's just like my general advice. Don't reinvent the wheel. So this is a really interesting, not reversal, but observation that we're learning more about these models to the point where we don't need them to keep getting bigger forever, and that just being bigger does not necessarily make things better. And I am not deep enough in the computer vision literature to know that that's a case. I know that there has been work on sparse transformers in computer vision as well, which is sort of an extension of this. But it's interesting, and it's exciting to me because it says that transformers, in addition to the benefit of training time where you don't have sort of sequential limits on parallelization, you could get better results with smaller models. And like I said, I love small things. Anyway, I think just within, it's helpful to place this within a larger context, because the idea that removing things would improve performance is not intuitive, especially given computer vision work on CNNs and then all the NLP work using RNNs. New family of models. Given the complexity of language and amounts of pre-training data, it is not clear why BERT ends up with redundant heads and layers. Clark et al. 2019 suggests that one of the possible reasons is the use of attention dropouts, which causes some attention weights to be zeroed out during training. So like they're not quite dead neurons because they're not necessarily going to propagate up the rest of the model, but they do get turned off, basically. BERT compression. Given the above evidence of overparameterization, it does not come as a surprise that BERT can be efficiently compressed with minimal accuracy loss. Such efforts to date are summarized in Table 1. So there was a question earlier about what I'd recommend using other than BERT, some smaller ones. So a lot of work on distillation, DistilBERT, BERT PKD, BERT 48, 182, TinyBERT, MobileBERT. That's perhaps obviously for embedded systems. PD, MiniBERT, BiLSTM soft. Oh, interesting. Quantization, which is used in Convert as well, which is the conversational AI, conversational representations with transformers. Sorry, sirens. QBERT, Q8BERT, and then other Albert base, Albert XX large, and BERT of Theseus. I sort of like know that Albert exists, but I don't know what's special about it. I know that it's small, and I think it's by the same research team as well. I think it's by that same Google Brain team. Comparison of BERT compression studies. Compression, performance retention, and inference time speed-up figures are given with respect to BERT base unless indicated otherwise. Performance retention is measured as a ratio of average scores achieved by a given model and by BERT base. The subscript of the model description reflects the number of layers used. 1 star means they use a smaller vocabulary. 1 dagger means the dimensionality of the hidden layers is reduced. 2 stars means the dimensionality of the embedding layer is reduced. Double dagger, I don't know what that is, compared to BERT large, and then squiggle guy compared to MBERT. That's multilingual BERT. And as you can see, you can have compression up to 110 times larger. Wow. Okay, maybe this paper should be on my to-read list as well. You can have speed ups, anywhere from twice as fast to 400 times, and still with more than 90% of the overall performance. So you get pretty much the same bang for way less buck. And then the model that it's compared to, and then the evaluation tasks. Scrolling up. 2 main approaches include knowledge distillation and quantization. The studies in the knowledge distillation framework, Hinton et al. 2015, use a smaller student network that is trained to mimic the behavior of a larger teacher network, BERT large or BERT base. This is achieved through experiments with loss function, mimicking the activation patterns of individual portions of the teacher network, and knowledge transfer at different stages in pre-training or at the fine-tuning stage. Interesting. Distillation is one of those things I know exists and I have never done, so lots of knobs to play with there, it sounds like. The quantization approach aims to decrease BERT's memory footprint through lowering the precision of its weights. Shen et al., Zephyr et al. Note that this strategy also often requires compatible hardware. Yes, that makes sense. Other techniques include decomposing BERT's embedding matrix into smaller matrices and progressive model replacing. Zhu et al. 2020. Oh, interesting. Okay, so that must... Oh, like the ship of Theseus. Oh. That's like the story where... or like Abraham Lincoln's axe, sort of same thing. You replace... Like if you have an axe and you replace the head and then you replace the handle, is it the same axe? Or if you have a ship and you replace it board by board, is it the same ship? Yes, I guess. I don't know. I don't have a lot of patience for that sort of philosophy nonsense, but it's a cool idea. Multilingual BERT. Multilingual Bert, Mbert, is a version of Bert that was trained on Wikipedia in 104 languages, 110K word piece vocabulary. If you saw that the original version was 102 languages, they've added Mongolian and Thai, so hence the difference. Languages with a lot of data were subsampled, and some were super-sampled using exponential smoothing. Super-sampled using exponential smoothing. Don't know what that means. Anna says, an unsolved problem with overparameterization is that while Bert can be pruned, so you can remove stuff, equally performing smaller Berts haven't been trained for scratch. Okay, so how do you get the same amount of bang for less buck? You can take the big buck and remove, I don't know, my metaphor is falling completely apart. Voida et al. 2019 had that experiment for Transformer in general. Okay, so something about the architecture is letting us learn what we need to learn, but also there's a bunch of wasted space. Mbert performs surprisingly well in zero-shot transfer on many tasks. Wu and Dredzi, Pires et al., although not in language generation. The model seems to naturally learn high-quality cross-lingual word alignments, Libovicki et al. 2019, with caveats for open class parts of speech, Cow et al. 2019. Adding more languages does not seem to harm the quality of representations. Okay, so have not read the Mbert paper, but it looks like it is sort of similar to the zero-shot cross-language word representation embedding research that's been around for a while. I think Facebook also had a really big research project similar to this. Some of these people might be from Facebook. I'm not super knowledgeable about this particular area of NLP. Mbert generalizes across some scripts, excuse me, and can retrieve parallel sentences. Excuse me? So generalizing across some scripts would be like, you could do Arabic and Latin script with the same model, which is, wow, surprising. Yeah. Although Libovicki note that this task could be solvable by simple lexical matches. Pires et al. Conclude that Mbert representation space shows some systematicity in between language mappings, which makes it possible in some cases to translate between languages by shifting the representations by the average parallel sentence offset for a given language pair. I'm assuming we're going to get to figure 7 soon. Mbert is simply trained on a multilingual corpus with no language IDs, but encodes language identities, and adding the IDs in pre-training was not beneficial. It's also aware of at least some typological language features. Has some statistical correlates of those features, I would probably say, and transfer between structurally similar languages works better. Interesting. Singh et al. Argues that if typological features structure it represent... starting again. Singh et al. Argue that if typological features structure its representation space, it could not be considered an interlingua. However, Artexta et al. Showed that cross-lingual transfer can be achieved by only retraining the input embeddings while keeping the monolingual Bert weights, which suggests that even monolingual models learn generalizable linguistic abstractions. So the reason that this is important is if you just have all languages in a single feature space, but you can't take French and move it to Vietnamese, that's not useful for cross-lingual tasks. And this suggests that you can actually do that for things like translation and data augmentation for low-resource languages and stuff like that. At least some of the syntactic properties of English Bert hold for Mbert. Its MLM is aware of 4 types of agreement in 26 languages. Mass language model. Okay, so I'm guessing this is where they did the probing study and would be c'est une femme and looking for jolie with the correct gender marking. Wow, that took a while to pull up. And main auxiliary of the sentences can be detected in German and Nordic language. Main auxiliary of the sentence. Okay, that must be the main auxiliary verb, I'm guessing. I do not speak German or any Nordic languages, so I'm not super familiar with the grammatical structures there. Pires et al. And Wu and Dredzi hypothesized that shared word pieces help Mbert. Based on word pieces is what's used for the tokenization. Based on experiments where the task performance correlated with the amount of shared vocabulary between languages. Oh, maybe it's not the... However, Wang et al. 2019b dispute this account, showing that bilingual BERT models are not hampered by their lack of shared vocabulary. Okay, so it's not just like there's a lot of cognates, like words that are very similar between languages. Arteche? I have no idea how to say that. My apologies to this person. Also show that cross-lingual transfer is possible by swapping the model vocabulary without any shared word pieces. To date, the following proposals were made for improving Mbert. Fine-tuning on multilingual datasets is improved by freezing the bottom layers. So you can't change any of the weights on the bottom layers. Improving word alignment and fine-tuning. Word alignment between languages? Translation language modeling is an alternative pre-training objective where words are masked in parallel sentence pairs. The model can attend to one or both sentences to solve the prediction task. Okay, so like, I'm trying to come up with like a good example. Like if you had to say, the cat chased the mouse in English, and then you masked mouse, and then the same thing in a different language, and you masked the word for mouse there, and you could use either sentences information to figure out what the cat was chasing, or to predict the word that it should be. Huang et al. 2019 combined 5 pre-training tasks: monolingual and cross-lingual masked language modeling, translation language modeling, cross-lingual word recovery, and paraphrase classification. A fruitful research direction is using monolingual BERT directly in cross-lingual settings. That is good because some languages have a lot more data available for them and for training large models than other languages. And English is the juggernaut that just squishes everybody else's languages, and it's kind of a problem. And the benefit here is that you could use the fact that there's a really uneven distribution of resources to create resources that are usable across languages. Clinchat et al. Experiment with initializing the encoder part of the neural machine translation model with monolingual BERT weights. So I think Gutham had questions about it, so that's one way of doing it. Arteche et al. And Tran independently showed that Mbert does not have to be pre-trained in multiple languages. It is possible to freeze the transformer weights and retrain only the input embeddings. Freeze the weights in the transformer and retrain only the input embeddings. Okay, so that's like the token input. And I think the positional embedding is also trained for... Again, I don't get the positional embedding for the original BERT. I'm sure there's a good reason. I was not super convinced by the paper, and it could be that I just lack the relevant background. All right. Yeah, I think we're going to finish that up. We have one more section, and it is discussions. 1 page. Limitations. As shown in section 4, multiple probing studies report that BERT possesses a surprising amount of syntactic, semantic, and world knowledge. Possesses statistical correlates of syntax, semantics, and world knowledge. However, as Tenney et al. Aptly stated, the fact that a linguistic pattern is not observed by our probing classifier does not guarantee that it is not there, and the observation of a pattern does not tell us how it is used. There is also the issue of trade-off between the complexity of the probe and the tested hypothesis. A more complex probe might be able to recover more information, but it becomes less clear whether we are still talking about the original model. I guess this would... The correlation for human here would be if you ask extremely leading questions, you can get the correct answer, but it's not clear if the person knew the thing. Not that we should talk about BERT like it's a person, because it's not. Furthermore, different probing methods may reveal complementary or even contradictory information, in which case a single test, as done in most studies, would not be sufficient. Certain methods might also favor a certain model, e.g. Roberta is trailing Bert with one tree extraction method, but leading with another. Head and layer ablation studies inherently assume that certain knowledge is contained in heads' layers, but there is evidence of more diffuse representation spread across the full network. Full network. Also, I've recently learned that I have the pool merger sometimes, especially when I'm feeling informal, and it's just surprised me deeply because I did not think that I did. Let's restart that sentence. Head and layer ablation studies inherently assume that certain knowledge is contained in head/layers, but there is evidence of more diffuse representations across the full network. The gradual increase in accuracy on difficult semantic parsing tasks, the absence of heads that would perform parsing in general, and the absence of heads that would perform parsing in general. Ablations are also problematic if the same information was duplicated elsewhere in the network. To mitigate that, Michel et al. 2019 prune heads in order to set by a proxy. Prune heads in the order set by a proxy importance score, and Voigt et al. 2019 fine-tune the pre-trained transformer with a regularized objective that has a head disabling effect. Okay, so ablations are where you take parts away and you see how the model do, and part of the problem is this redundancy in the model, so there are some strategies that you can take to avoid that. Many papers are accompanied by attention visualizations with a growing number of visualization tools. However, there is an ongoing debate on the merits of attention as a tool for interpreting deep learning models. Also, visualization is typically limited to qualitative analysis and should not be interpreted as definitive evidence. Gutham says, if there's anything I've learned, it's that way too many researchers have spent a lot of their time on this one model. I don't know that that's necessarily the case, because transformer language models are just like transformers in general. They're here. We're using them for NLP, like we're using them at Rasa. I think it's important to have a deeper understanding of how and why they work and what we can change and what we can't change and what the effects of those changes are. So my background is more in science than engineering, and one of the things that I find most frustrating about deep learning in particular is that we don't have a good understanding, particularly of newer classes of models, of like what different parameters do, like what different seeds do. Clearly they're doing something separate. I don't think you shouldn't tune your seed. That's not a thing that you should do. But we know that they are making changes and not necessarily what those changes are. And I think this deeper understanding of how these models work and what information they are encoding is really important, particularly if you're going to be productionizing stuff. So, Andre says there's so many open questions. Oh yeah, absolutely. If you're looking for a research topic, this might be a good one. Directions for further research. BERTology has clearly come a long way, but it is fair to say that we have more questions than answers on how BERT works. In this section, we list what we believe to be the most promising directions for future research, together with the starting points that we already have. Benchmarks that require verbal reasoning. While BERT enabled breakthroughs on many NLP benchmarks, a growing list of analysis papers are showing that its verbal reasoning abilities are not as impressive as it seems. In particular, it was shown to rely on shallow heuristics in both natural language inference and reading comprehension. So basically like statistical cues, basically. As with any optimization methods, if there is a shortcut to the task, we have no reason to expect that BERT will not learn it. To overcome this, the NLP community needs to incentivize dataset development on par with modeling work, which at present is often perceived as more prestigious. Here. I am consistently distraught with the downplay of the importance of data collection and curation and dataset and task creation. Developing methods to teach reasoning. While the community has has success extracting knowledge from large pre-trained models, they often fail if any reasoning needs to be performed on top of the facts they possess. For instance, Richardson proposed a model to teach BERT quantification, conditionals, comparatives, and Boolean coordination. Learning what happens at inference time. Most of the BERT analysis papers focused on different probes of the models, but we know much less about what knowledge actually gets used. At the moment, we know that the knowledge is represented in BERT does not necessarily get used in downstream tasks. As starting points for work in this direction, we also have other head ablation studies and studies of how BERT behaves in a reading comprehension task. So one that I think BERT does pretty bad at is the Winograd schema. Vinograd? I don't know if it's supposed to be a Y or a V. But that requires, I think that would probably be more the teaching reasoning than the looking at what happens at inference time. And this, I think, is also particularly important for learning about security vulnerabilities, because we know that these models have them, and we know that we don't know what all of them are, and we should. And ideally, the research community learns about that first. Conclusion. In a little over a year, BERT has become ubiquitous baseline in NLP engineering experiments and inspired numerous studies analyzing the model and proposing various improvements. The stream of papers seems to be accelerating rather than slowing down, and we hope that this survey will help the community to focus on the biggest unresolved questions. Neprased says, what means verbal reasoning? Good question. Let's see if there's specific tasks. So reading comprehension would be like answering questions about a reading passage is a good example, or like I can't come up with other good examples at the top of my head, but Gutham says, head ablation study sounds scary. A little bit. That's okay. Bert has plenty. It can lose a few. All right. So, and then lots of references, very helpfully. I don't think an appendix. Nope. So, really good paper. I really enjoyed it. This was very helpful. Definitely the attention studies are something that I've not been paying particularly close attention to. So very useful information there. Just like a quick recap, you can get statistical correlates of linguistic information from BERT. It's not grounded, and it's not doing things like humans do, which I think is good to know. Attention, it looks like a lot of the heads are, I don't know, I guess like a key point from here would be that fine-tuning is turning heads off and teaching BERT what to ignore rather than changing the representations of linguistic form, basically. Layers, different layers do different things. More layers seems to be really important, more important than the number of attention heads. Pre-training is maybe actually not as important as we thought, which is great because that's the expensive part. But it does seem to be doing some things. You do not have to use exactly the same tasks that they did. And you can have a much smaller model and pretty much the same performance, but it seems to be, as one of Anna's comments, it seems to be the case that it's hard for us to create a small model that on the first, after training, will have the same performance as a pruned version of a larger model. So, Anna says, I usually mean high-level verbal reasoning tasks, reading comprehension, natural language inference, and common sense reasoning. Okay. Thanks, Rachel. It's a bit awkward to talk over the live stream. I can't type fast enough. Yeah, no, I understand that. And then the conversation would also get unreadable without the video. Oh, I'm also pretty used to like there being a weird lag between people in the chat. So I didn't comment much or we wouldn't have gotten to the end of the paper. Fair enough. This was very instructive. We're researchers, only used to talking to researchers, and it's extremely helpful to see how this stuff actually gets read, used, and interpreted by the practitioners. Yeah. And Nepersed said, any real-world applications using this? So probably the best-known application of BERT right now is that it's been used in Google search. So BERT, the model, so Transformers, which were the family of architectures, was developed at Google. BERT was developed at Google, and it's been implemented in Google search. And I think like 10% of searches right now will use the BERT model instead of the thing that they were doing before. Question, a lot of the points in the paper were a bit cryptic, so when you read surveys, what would you rather have? More details from individual papers, easier to read, don't need to look elsewhere, or more papers covered, broader perspective, potentially more reliable data? It's a good question. I think I personally would rather have more papers covered, because right now when I'm reading NLP research papers, the bigger problem for me is knowing which papers are relevant and important, because there's a lot of publishing that's being done, and things on archive are of very mixed quality. And I also feel fairly comfortable going and reading the papers myself. Yeah, I think that a deeper description of different papers would probably be more of like something that I'd expect in a blog post, and then I'd expect a much more like focused description, like only about distillation in BERT, for example. But actually I would prefer the former, so I think it'll depend on your audience a bit. All right, I'm gonna call it there because I've got so much other stuff to do today. Thank you for joining me, everybody. I hope this was helpful and informative. I certainly really enjoyed the paper, very helpful for me, and my understanding of BERTology as of, I don't know, like a couple months ago, probably pretty different at this point. I'm looking forward to learning more about these models and seeing just how small we can get them. And I will see you all next Wednesday, and we'll be coding again, probably. And it seems like the paper reading has been pretty popular, so me and a couple of the other developer advocates are talking about how we might do this going forward. Also, I would like to read more papers, so. All right, thanks for joining me. Have a great day and enjoy your weekend, and I will see you on Wednesday. Bye.